Hi there, Physics 131. This is the pre-class reading video for class 17. It's sections, we're in chapter 6 on momentum. Section 6.3 is on impulse and momentum. So we've already defined a new quantity called momentum in the previous section. When you have an object moving along, it has some momentum, which is equal to its mass, which is a scalar, multiplied times its velocity, which is a vector. And the units of momentum are kilograms times meters per second. So now we have a new quantity called impulse. So if there's a force exerted on a single object, you say that you're applying an impulse to that object if it goes over some time. So they talk a little bit about acceleration, changing the velocity. And so they're just rearranging Newton's laws a little bit. And they define here the impulse of a force is the area under a force versus t graph line. So if you don't apply a force to an object for a while, and then at t initial, you start to apply some force in Newton's, that goes up and then goes back down again. And then t final, you stop applying a force. So imagine you give something a shove or hit it or something. Then there'll be the time before t initial where there's no force and after t final where there's no force. But the area under this curve is the impulse. And they say here that the area of the shaded rectangle, where the top of this rectangle is the average force, is about the same as the area under the curved line. And that equals the impulse. So rather than try to find the area of a curved line, what we do is we just say the impulse is equal to the average force multiplied times the change in time. So there's a new quantity now. Remember the letter P, lowercase p, is for momentum. Uppercase J now is used for impulse. So it's getting a little confusing here, but just try to kind of memorize or write down what the quantities are. So J, the impulse, is a vector. It's equal to this average force, which is a vector, times the scalar, which is the change in time, delta t. And the units are newtons times seconds, because newtons from the force, seconds times the delta t, kilograms. So actually, newtons is kilograms meters per second squared. You times by seconds, you get kilograms meters per second, which is the same as the unit for momentum. So that's the impulse momentum theorem, actually, is that when you have an impulse in a system, it equals the change in the momentum. So P final minus P initial equals the impulse. So that gets used a lot in this course. Impulse momentum equations, very important. I don't know why they shoot an apple with a bullet. But here's this one, example 6.2 is a good idea. Abrupt stop in a car. A 60 kilogram person traveling in a car that is initially moving with 16 meters per second hits a barrier and then stops. Determine the average force. So the stopping time is 0.2. What's the average force? Well, you can use the impulse momentum theorem here to say you've got the initial momentum plus the impulse equals the final momentum. You can solve out for what the force is if you know the time of the collision. You get 4,800 newtons. So it's just a nice way of solving problems a little more quickly and thinking a little bit about momentum. This one is saying, so you got a collision of two carts, cart 1 and cart 2, and during the collision they push on each other with some spring. And the idea here is that the impulse of 1 on 2 equals negative the impulse of 2 on 1 because of Newton's third law. So that's why the two impulses, if you consider the entire system, they'll cancel out. Those are internal impulses. So you get that the initial momentum of the system of both carts equals the final momentum. So that's where actually conservation of momentum comes from, is because internal impulses in a system cancel out. Section 6.4, generalized impulse momentum principle. Basically, it's just this this equation 6.8 is one way of looking at things. I guess they just say, actually they split it into x and y components. It's all the same equation. The initial momentum, which is the sum of all the m times the v's, plus the net impulse exerted on the system equals the final momentum of the system. So, and the equations themselves look a little messy. So what they do in the textbook, which I like a lot, is they introduce these bar charts. And what those do is it gives you kind of a visual way of looking at the equations. So, so you got, initial momentum of the two objects plus the impulse equals the final momentum. So you can imagine all of those terms as being positive or negative bar charts. So this plus this equals this final. So there should be as much area kind of on the right-hand side as there is on the left-hand side of the equal sign. So you've got 3 up, 1 down. That's like 2 up, and those get split between the two carts. And what you're doing there with that momentum bar chart is representing two carts. One's moving faster to the right than this one is moving to the left. When they collide and stick together, they both end up moving to the left a little bit. So good to try these. This is happy ball versus sad ball. I might try to bring one of those to class. But basically some things bounce and conserve kind of their motion or kinetic energy, and some things don't bounce, but they still have to conserve momentum. But they just do it in sort of different ways. So I would read through that, and that's it for Wednesday's reading. Okay, take care. See you in class.